이제 또 히트하고. Sono certo che o da Okumani will be in the video. As you can go down and just a small detail. Ela acho que me lembra assim, e até que eu plástico na aula de plástico para o geen dingen moet er zelfs ook doden. Oi, não büyüsü siklet yapın. İyi ceza mı This is just literally earning engineering cost. Are you writing anything there? Have you already prepared some questions for our exam? Yeah, of course. So now, again, I like this style very much. Not really yet. We have only 2 chairs left. We got 6 chairs then. No, you won't. Because this one is just for your brand, it's a review session. So we just talk about something about the event. Previously we had about 5 lectures, roughly 10 hours. But in the previous materials, probably they have too many examples of too many cases, and in different cases we have different assumptions. And based on the different conditions, we have different methods to define the result. So after I went through all the materials, I found that it's really confusing. So today I will use three very typical questions, and I will just go through the solutions that you know how to solve the typical problems. I think they will make us clear today. Actually, if you go through the whole all the materials in my part, actually we just focus on 3 or 4 points. If I do a summarize now, I would like to introduce the Morrison's equation first. And actually, when you finish all the calculation cases, you will find that no matter when you try to find out the mean force or the wave force, actually all of them, they are based on Morrison equations, but they use different terms. Well, if I start with wind force, we know that usually if you have a question asking you to calculate the wind force acting on this structure, we have a velocity average, right? So if we go back to Morrison equation, you will find that here is the wind speed, and we can use the wind speed for the second term. For the first term, because we have an acceleration part, but now we don't have anything about acceleration. We just have an average speed. It means here will be 0. It means the first term will be 0. That's the reason why when we calculate the wind force, we use an expression like half density, drag coefficient, acting area, and speed square, right? So if you look at the expression carefully, it's the second part of Morrison equation. Well, about the velocity, of course, it's the average speed of the wind, and about the density, of course, it's wind, and we use the density of air. You can use the value 1.225 or 1.23. That's fine. It's kg per cubic meter. And I think in your exam papers, if you need this density, I will not give you the values because it's a very basic value. So you can use a value like this. It's fine. And when you use the density of water, you can use 1,000 kg per cubic meter or 1,025. That's fine. Both of them will be okay. But anyway, it's very straightforward, right? After you know the density, you have a good drag coefficient, you have wind speed, but when you try to find out the acting area, according to different rules, we have different methods. And if you can still remember that, we have, I showed you 2 different rules. The first one is the API rules, and the second one is the example from ABS. So by different rules, we have different methods to calculate the acting area. But now, please just forget the ABS example, because in most cases we use API. But in your work, because you are going back to probably different ship societies, you will have different rules. But here is the most typical one. For this one, we used to have an example. Here is the platform, and we also have a deck house here. And well, this one. So in the calculation, in our examples, you can see that when we estimate the acting area A for different things, this part, and for that cost, we use different ways, right? The reason is, for this structure, we assume that it's a porous structure, and the wind is coming from this way, and after acting on the surface here, it will go through the structure and acting on the backside again, right? It means if the acting area is 100, we need to consider twice the face area. And then because it's a porous structure, it will generate a lot of turbulence. It means this part of effect we cannot ignore. It means
we also need to think about the force acting on the side. So that's the reason why, after you know the side surface, the area, we need to add this part. Because we have another side, we need to add them together. So the first part is for this acting area and the back area, and this part is for this side and the other side. Okay? That's the reason why you can see a calculation here, and we are following the API rules. But for deck house, it will be a solid box. We don't open doors and windows when we do OpenSea works. So it means when the wind is coming from this way, it will not act on this way, on this face again, right? So that's the reason why we just use you just use 20 for the acting area. It's the face area, right? If you go back to the equation, the face area of that house is here. That's the reason. And because it's not a porous structure, it means we will not generate a lot of turbulence as the structure here. It means we don't need to care about the turbulence acting on the side surface. That's the reason why we just use 20 as the acting surface. So in the calculation, you can see that for the deck house, the acting area is here, but for the structure or the other parts of this platform, we use a very big acting area. Okay? And then after you have A, we go back to the expression here. And for different things, you have different drag coefficients from that table. You will have a table. And then if you add them, all the terms together, you will find out the total force on the structure. But please remember that we can follow different rules, and if you follow different rules, for example, in our previous cases, we followed API rules, we followed ABS rules. Actually, we also have the rules from Lloyd resistor or CCS in China. After you finish the calculations by different rules, you may find that the result could be completely different. That's quite normal. So at this stage, you can see that we use a very simple estimation. But afterwards, if you carry out CFD study for the same thing, probably you will have another result. And if you do a compression, you will find that the result from CFD will be completely different with all the estimations here. It's also quite normal. And even afterwards, again, you do an experimental study. For example, in wind tunnel, I believe you will have another different result from the result in CFD. That's also quite normal. So you can only carry on. And by this stage, we trust the result from the experimental study. But after you build up the structure and you just use it in OpenSea, this time you can measure the forces. And then you can go back to the estimation here and you can correct your rules and you can correct the drag coefficients. And then that's the reason why it's better and better. But now, by this stage, when we do estimation, we just use it. Okay? So I think about wind force is clear now, right? So if you carry on the calculation, I think you can have at least similar result like I did.
Question, on the exam we will have just only API and we need to calculate this API.
You can just follow API, yeah. Forget the APIs. By that case, I just want to show you we can have different results by different rules. So wind force.
Do we need to remember the coefficients for the buildings?
Sorry?
Do we need to remember the coefficients?
No, you have a table. But you need to know for different parts you have different coefficients, and you need to select the best one from the table.
Okay.
Well, the next point is about wave. The first one thing, if we still start from the Morrison's equation, we should know that in open seas, when we calculate the wave force on a structure, usually this time we have the acceleration part, right? But actually, if you compare the two parts from the two terms, usually this part, the value is very small. So in estimation, in most cases, we don't care about the drag force. And in terms of waves.
Can you repeat this? Sorry.
Why you said it? Can you repeat again?
Sorry?
Can you repeat this side?
We missed just
Yeah, we missed.
your drag force.
Well,
Why not calculate drag force?
we should apply Morrison's equation if your structure is quite small compared to wavelengths, you know that, right? But when we apply Morrison's equation, if you calculate the initial force, when you calculate the drag force, and you do a compression, this part is usually very, very small. They are not at the same level. So we don't do the calculation here. It's wasting of time. That's the reason why I just deleted. That's the reason why in all the cases, you can't see the calculation for drag force when we talk about wave, okay? So if we just look at this part, the first term, and I think you can see that it's from the Newton's law. The force is the product of mass and acceleration, right? If you look at this expression carefully, here is density, here is the volume. So the product of the two terms is the mass here. And here is the acceleration is here. And this means the differential operations for velocity over time. But now you can see that we have a coefficient. But in this principal law, we don't have the coefficient. That means we actually have a different part or have an additional part. Here is the original expression, right? The mass, the acceleration, but we should add something. And this part is for added mass. And for added mass, we have a coefficient here. But in most cases, we combine them together and we use Cm. That's the reason why you can see an expression here. But anyway, you should know that we cannot apply this directly. We should add something. because when you try to move, you need to bring some water together with you. It's like your weight is a bit greater. And when you use your weight, we use a more practical one with the added mass. Okay. Well, in my previous materials, I think you can see different expressions or different explains for the total force. But if you look at them carefully, I think it's just here. And because on the whiteboard, we don't have the drag force part because I said it's too small. I just deleted. So we have only two parts for the total force. And here is for added mass, the second term over there. And here is for the principal expression. Okay? And actually this page is from Professor Longbin, and I think probably it was from 10 years ago. So you may have some very confusing names for different terms. So after I give you this part or this page, you can just ignore them. We just need to know when you do the calculation for force or for acceleration, we use a different mass. The real mass of your structure and the added mass from your, you can estimate the coefficient from the table, okay? But again, if you apply different rules, you may have different coefficients. So now, another important thing is when you talk about wave, we need to know the expression for wave surface. In my part, well, in this module we have two parts, and the other one is from Dr. Wen Xian. In my part, you don't need to remember how to write this, but if you see an expression like this, you need to understand all the terms in this expression, like what's this? And of course, you can have a table here, and the first figure is for this expression. We need to know the wave height, right? And we need to know the wave number. We need to know the wave frequency. And for definitions, of wave number and wave frequency, for both of them, we use 2 pi as the reference value. If you know the wavelength and in every 2 pi, how many waves you have, that is your wave number. Okay. If you know the wave period of a single wave and in the time of 2 pi, how many waves you have, that is frequency. Okay. And of course, again, you can find that from the table. So you don't have to remember this, but if you see some expressions like in the table, you need to understand what's that. Another important thing before we calculate any forces from waves is the speed potential or velocity potential. And for the expression, I think we have a very good one from the table. Where is it? This expression is based on the assumption that the water depth is very high, the value is great. So we can have a simplified expression here. And in our calculations, because it's for open seas operation, and we always assume that, at least in my part, we always assume that it's for deep sea. So we can just use the expression in deep water. Okay. But after we have this potential function, we need to know that if you do a differential operation against x, we will have the velocity in x direction. After you have the potential function over there, you can calculate what is the velocity in your horizontal axis or in x direction. Okay, and again, after you have the velocity, if you do another differential operation over time, it means you know the acceleration in x direction, right? And you can find the expressions for u and expressions for acceleration in your formula table. But I think in the table we don't have the expression for the velocity in z direction. But actually we can do the calculation by yourself in the same way. And then after you have v in z direction, it will be the acceleration in z direction. So actually, after you have the potential function, you have the velocities, you can have the accelerations in both directions. Okay? And in this page, I think the most important thing is here. After you have the wave, of course, we always want to know the response of your structure, of your floating structure. And actually, you can just apply this expression for the response in z direction. And if we don't have the damping force, it means the damping ratio is 0. It means we can simplify the expression like this. And again, if the damping ratio is 0, it means phi is 0. The phase angle is 0. If we come back to this expression, phi is 0. So we can simplify the expression again. But even we have a very simple expression, we still have to find out what is f, what is k, and what is natural frequency. You can find the expressions for all of them from the table. Okay. So now, if we come to this very typical question, can you use 2 minutes to look it through. In my previous examples, I did have a mistake in calculation. I think it's 6, but in my calculation, I used 5. Sorry about this. I just found this yesterday. So in this question, we have a platform with 4 columns and 4 bases. And we know the details of your wave, and we want to know the heel motion, right? The motion features in Z direction. So, as we know from the expression in your formula table, we can have a very simple expression here. And then actually we need to find out what is F, what is K, and what is natural frequency. So according to the formula form, I think we can just find out what is K. You have an expression in your formula form, okay? And the AW is for your water surface area. And I think we need to remember that we have 4 columns, right? About natural frequency, if we know the stiffness, we can just use it in the expression. And we know the real mass because you know the displacement, because you know the geometrical features of the structure. And by the formula form, we also know how to get the added mass, because in the last page, is that last page? Oh, page 4. We have 2 estimations for added mass. The first one is for heel motion. The second one is for horizontal motion. Okay, so this one is for heel motion, and you can use the first expression in that form to estimate what is your added mass. And because you have your geometrical features of the structure, we will know the real mass. So add them together, it will be the mass you need for your calculation. Okay. So here it's from the calculation here. Here is your real mass. Here is your added mass. So by these 3 terms, we will know the natural frequency. So if we go back to the expression here, phi is 0. Now we know the natural frequency. We know what is stiffness. The last one thing is we need to find out what is the force in Z direction, and then we can just estimate the response, right? And in this page, in my previous calculations, as I said, I had a mistake. I think it's here. It was 5, but now it's 6. Okay. So when we think about the vertical response, we should have a force like this, and we should have a force like this, and the combination of them will give you the vertical response, right? And because in Morrison equation, again, we don't think about the friction force or the drag force. So actually we just have the two. The first one is from bottom, the second one is from the top. That's the reason why you can see two different calculations. From your formula table, we have an expression for your pressure, right? In the first page, the bottom one. And you can see that we have two parts. The first one is rho gz or something. But please remember that this is static force. It will not give you response. That is what is just for your buoyancy. That is the stable part. But we have the dynamic part. That's the second term. This term will give you the response because it's always changing. So, after you know your waves, you can just apply the dynamic force on the center point. That's the pressure on this point. And because it's acting in this way and the diameter is quite small compared to the wavelength, so we can just assume that on the whole surface, the pressure is all the same. So after you have the pressure on this point, and after you know the area, we will have the force. That's the basic idea, right? And again, after you know the pressure here, we can assume that on this surface, all the same, on this surface, all the same. But please remember that the acting area is just this circle. That's the reason why you can see something like this, right? If you have, after you have the force on bottom, after you have the force on the top, they are in different directions. That's the reason why you can see here you have minus sign. Because in our coordinate system, we use something like this. So the force on top will be like this. That's the reason why you can see a minus sign. And I think I had a mistake here in my previous lecture. I put the minus sign over there, but now I correct it. But anyway, after you have the total force, you know the total force, you know the natural frequency, you know the stiffness, and you can just go back to the expression here, right?
Instead of natural frequency. Natural frequency. So we found natural frequency.
Here, natural frequency, yeah, we have finished already. Well, again, because we don't have the damping force, and the damping ratio is 0, so the phi is 0, so we just have omega t, right? And we know F, we know K, we know natural frequency. in the end, you can have the expression for the response. Okay? And because you can see that from the final result, because we have the wave and we use the cosine function to present the wave, the response again will be a kind of cosine function.
That cosine function comes from the f, from the result of the f.
It's from the expression for the vertical response.
Yeah.
It's here. So you can just apply this in this way. So the previous example is for the vertical response or the vertical force. And the condition we can apply Morrison equation is the structure length is very small compared to wavelength, right? And we can just assume that to this disk, the wave is like this because it's very big. That's the reason why we can assume that on this point, after we have P, we can assume that on all the area we can use the P. But if we have a question in this page, we have a simplified platform and we have only 2 columns. Now my question is, I have a wave and of course you have the force in this way. And my question is, please tell me the response of the surge. This time, can you assume a pressure here and assume that all the same? I don't think so, because we know that the change of wave force along with the water depth will be like this, right? The change is a lot. So of course this time we need to do an integration along with the depth. That's the reason why in some cases we can just use P multiplied by area, but in some cases we must use the integration. That is because the change is too much. So by this point, I think I can give you another example. If my question is, please tell me the vertical response of this pillar now, can we assume that here is P and the force is P multiplied by A? Yes, we can. But if I put the pillar in this way, can we do that? I don't think so. Because you see, along with this wave surface, we will have a different force. So if in this case, we need to do the calculation in this way. Even your diameter is very small, but probably you have a 30 meters long pillar, right? And 30 meters to a wave is not small. So we must do the integration. But Now my question again. If it's a vertical column and I want to know the horizontal response in this way, we need to do integration, right? Along with dz, because your depths change a lot and the force change a lot. But this time, if it's like this, do we need the integration? No, because it's quite small and we can assume that the force is PA. That's the difference, right? So if you go back to the previous examples, I think this time it will be clear, right?
Oh, it's alright.
Sorry?
Go ahead.
I still have that on my paper.
Excuse me, what is the criteria to decide whether or not we approve?
Usually, when you apply Morrison equation, we use D or L against the wavelength, and if the ratio is smaller than 0.2, it means we can say it's small. But in my part, I would stress if you have a vertical one like this, we always use the integration because it's quite long. Okay, but if it's a horizontal one like this, if it's a horizontal one, it's okay. But it's in terms of horizontal response. So, if we still go to a Morrison equation, of course, no matter how deep it is, we will not change the density of water, right? So it's fine. And Cm, you know how to get the Cm from your formula set. It's okay. And this part, it will be a bit different because the acceleration will be a function of water depth, right? And if we do an integration, and here is, oh sorry. This acceleration, for example, here is Z. It's just for this element, right? And when you think about the volume, it should be the volume just for this element, right? And then we need cross-sectional area. We need the depth of that element. Here is the small element volume, right? And then if you do an integration, that's a force over the whole thing, right? So that's the reason why you can see the calculations in the following two pages. The first one page is for the force on the left one, and you can see that it's integration. And we need the cross-sectional area is here. And we need the depth of that small element, and we need to do the integration. We need the density, wind is the coefficient for added mass. And then here is the acceleration. And you can get this acceleration from your table. It's here. Right? And then you can have a final expression. If we apply this to the red one, we will have another expression, and after we add them together, it's the total force on this structure. If this structure has only 2 legs, it's just a showing case, okay? And you will find that again, it will have motion with time, right? Because we have this term. And we have density, we have added mass coefficient, the cross-sectional area, and the expression or the amplitude for the force. But about this part, we can change something by our design, right? Because it's, here is the geometrical feature of this structure. If we go to next page, if we have a good design, we can make sure the whole term is 0, right? That means this part could be 0. It means the total force will be 0.
So we just assume.
Yeah? So, according to our knowledge, it could be 0, right? If we have a good design or have a good value in this bracket. If it's half pi, it's 0, or several times of half pi is 0. But anyway, it could be 0. It depends on our design. And here is our wave number. It's from the previous question. You can't change the weather, but we can change our design. So if you have a good design, according to the definition for wave number, it's here. R pi. Oh, sorry. It's in Chinese. 2 pi over lambda. Sorry. 2 pi over lambda is the wave number. But anyway, if we put them together, we will know that in this design, if the distance is 2n plus 1 multiplied by lambda, it will be 0. If we go back to the whole expression, the total force will be 0. It means it will not have any horizontal motion, right? But actually, in real case, we don't have this one. But if just in mathematical ways, we can have this, okay?
So do we need to say that in the example? Do we need to write that in the example?
Right, what?
To write this design consideration about the force.
No, you don't have to do that. But as long as you have the final result, you tell me how to design this structure, and then in that case, you have the minimum motion. That's enough. Okay?
So when the design is perfect,
Yeah, when the design is perfect, it will be like this. And the scale or the size of your structure will be here. Okay? The reason we don't have this perfect situation in real operation is in open seas, we don't have only one wave in sine or cosine function. We have waves from different directions. If you can make sure in this direction it's perfect, but in the other direction probably it's wrong. So that's a reason. But anyway, today I went through how to calculate wind force, how to calculate the response in x direction, in z direction. I think it should be clear, right? So if you go back to other examples, I think it should be fine. But I have to say, in the other examples, I'm sure I still have some typos or even some calculation mistakes. But the basic idea is here. And I will try to find all of them out and correct them. Probably next week, or maybe after your exam. I will try.
So, is that on Blackboard already?
Yeah, I will just upload this. And before your exam, you still have more than 10 days, right? Because I don't have any lectures in the following 2 weeks, so if you have any questions, you can go to my office. Okay? And because it's my first year to take over this module, I know I made some mistakes, so thank you very much for your support.
So all the questions from your part, all the questions will be from the past papers, yeah? You are not going to any
I
new.
have no right to tell you that because I'm not the module leader. But if you can make all these 3 questions
You can
here
keep it in
clear,
secret.
you will decide. It's professional opinion, it's top secret.
You were saying if we were to calculate the heap response of the horizontal cylinder, we need to do an integration.
Yes.
But with respect to what, like, what is the differential of x or to z? The differential.
So when you do integration, in the
Should
horizontal
be-
direction, it's nothing about that. You can just assume here, and you can calculate separation.
But for the heap, for a horizontal cylinder, like the response, we should use an integration, right?
So, I think I've finished.
For
If we got wrong answers because of one tiny mistake, such as the
Yeah,
unit,
but respect,
can we got
the
0 or
the
something?
differential will be.
No, I will mark your solutions step by step.
So essentially, we just need these 3 examples.
No.
For your so we essentially just need these 3 examples for your side, and as long as we know these inside out.
Yeah, I think so. But I don't know.
No. That's only just from your
Because you change.
And in your exam, you need to answer all the 4 questions. It's compulsory. You just have 4 questions. You need to answer all of them. It's not like in the other modules. Because in some others you may have 6 and you select 4, but in this one you just have 4.
So we have 2 from the same.
Yes, up, yeah.
When can we find the last year's GMT source?
I sent the email to log in because I don't have the website for the system.
In all of my education, my 17 years in the exam where I have to do every question to the challenge.
You can find the exam papers from 2 years ago or 3 years ago.
This is why
for last year. You send me an email, right? You see my reply and
Yes, I saw that you emails to them.
Yeah. But
So there's no way I
it's really in China and last week. Now it is anyway, I will not
When I was doing this example, it says that for the short response, three equations should be applied. It don't repeat that all these these two terms are zeros. So from these terms, I don't know what is done in the response, the answer, but they have this equation. The question is where does this equation come from? So I'm sure this problem. I think it's this example.
Which question?
Wait until after fundamentals. Yeah.
We find one section. The priority is an equation that x equals x0 sine omega t.
I think it's because of course search and you have only
Exactly.
what's the search?
The question is where does the expression come from? Something that I should just learn by heart, or
It's not conventional.
that it might change.
Just before convention.
Oh, yeah, that's the problem. Yeah, if it comes into your conventional and then
But I was obviously you stood next to me because I'm good at when you, because you are, and when you're in the procedure, you will have the functions here from your meeting, so you don't have to really work out. Yes. Yes. Because it's for different. Most times,
No.
example 3,
Yeah, no.
how it's not.
Let me see.
I checked for
This thing. Where does this come from?
this app.
Because I understand that you are deriving this so you can get the acceleration.
there you go.
Earlier I was saying WhatsApp, but now
It's for us.
study time, no WhatsApp.
It's about how to get x is like 0 sine something by something y sine something. You mean how to get this from here?
Should I derive it back?
No, you don't have to write it out. I mean, I think it's quite easy to get.
Yeah, but my question is, why do you use this tool? Well, I see here.
It's like I read the question. I know where because I have gone through all the material.
If
The
x is
acceleration is in the x direction, right?
How can I say for all of them?
Oh, do you not write the
No. No, it's only oral studies. Like first question, I read and I know which slide to go to. Like and then first portion.
Acceleration, the x direction. Okay.
No, that's
Yeah.
Yeah, no, I know.
Also,
Yeah.
it's just oral.
Okay, so it's the other
No,
one.
writing down.
Misunderstanding. Why do you not understand the English?
200
No, like it's like which part of the lecture comes to
That's
this?
exactly what I mean.
That only I know.
All right.
Yeah, but still, from that, what extra has to be taken out is not. It's not my point.
Well, I think the reason why you need this is because you need the first differential operation and then get the second differential, and then this is the acceleration. You need to go back for this.
Which slide, which portion it comes?
But the question is where does this come from? Where this expression? Because I know that I derive it 2 times when I get it, but where did I get it from? It's something that I should know from other knowledge.
Well, I think it should be like this. When you look at the expression here, right?
Yeah.
Here is like a constant. Here is like a constant. Here is a constant. It's like something like this.
They make everything a constant.
Yeah, yeah. And assume that you have the amplitude first, and you have the function with time. Yeah. Your notebook.
Angel, do you know who does that?
Angel. Martin, is it yours?
Angel.
Angel.
You mean the
Aside
values?
this value,
Yeah.
we should
No, all the other constants or all the formulas will be from.
Do we need to print out the exam or you
No, you will have this in exam from the examiners. I think so. I didn't change anything.
I don't think one in this class is that where you go now, you can use other Nah, it's all materials now. You can't manufacture materials. Materials? I don't say. Yeah. I feel like I'm literally this after the.
What's your going to do after materials?
No, I'm not sure. No, literally after the materials now, and then just after the material exam, yeah.
Oh. In one day?
Have you seen how many little slides it is?
Thank you guys.
Thank you very much. No, no.
Are you crazy? Sustainability is 12 pages. Business candidate 12 pages.
Marketing 18 pages.
Exactly. That's literally
so
50
And
slides.
it's just, and you don't have to like get, and you know, if you to answer a structured question, you have to grasp everything.
Yeah.
But this is just looking through and you get the general overview, so that when you look at the question, you can easily tell this is the answer.
So budget, you don't need to worry about that. Just literally just worry about 07. This guy said this guy said that. And the finance ones, there's no calculations, that's perfect. You can discard so many slides, because all of them are just calculations. Bang, bang, bang, delete.
So these 5 days you're going to do materials.
Yeah, definitely.
How about fundamentals?
I've done mine already.
Exactly.
That's what we've
Done fundamentals and finish materials.
Past papers in fundamentals so important.
Minimum 2 questions always seem to come
For
up.
example,
Just it to-
in the one about the radiography of the defects, that it says, the axis says that is you should consider the circumference, not the diameter. Because you just take the diameter and divide it like 200 over 600.
So what?
You said where is the
Yeah.
where is the lack of fusion
And
is
then-
200
yeah,
millimeter.
exactly, for the lamella defect.
Yeah.
And you just took 200 over 600.
Yeah.
But the problem is that you're taking into consideration the diameter.
Yeah, might be. I said that not everything is correct.
No,
I told you
that,
again.
that's why I I think we should
Maybe.
get together.
Oh, you had done the question previously.
Yeah, I've done that. For me, my answer is that you can accept it.
You cannot.
You can, yeah.
But the answer is you can accept it as well. Which one?